Okay, let's continue with our discussion about the application of Faraday's law. One of the most important applications of Faraday's law is the so-called electric generators or motors. In an electric generator, you spend other forms of energy, such as mechanical energy or nuclear energy, to generate electricity, that is, to produce electrical power. And an electrical motor runs just the opposite way. What you do is you run a current through a device. Basically, you feed the system electrical energy, which then turns into mechanical energy by rotating. So that's called electric motor. So take a look at how electric generators work. Now, what I have here is something, in principle, quite simple. I have a coil. For simplicity, let's say it's shaped into a rectangle, and I put it in a magnetic field, in a uniform magnetic field, and I spin it about an axis. Okay, here is an axis passing through the middle, and I spin it about this axis at a high speed with angular frequency omega. Okay, what I want to find out is what happens if this loop or this rectangle is forced to turn in the presence of a magnetic field. Well, we can take a look at the side view. Okay. So what I have here is a side view. You have a pair of magnetic poles, north pole and south pole, and they produce a more or less uniform magnetic field in this region. And this is the side view of the rectangular loop we're talking about. So looking at it from this angle, basically. So it's like this, okay? And then we turn it about a certain axis, passing through here, okay, passing through here at an angular speed omega. Okay, at one particular moment, the orientation of the surface of the loop is in this direction, making an angle theta with the direction of the fixed magnetic field. You see, as the loop turns, the area of the loop facing the magnetic field changes, right? In fact, when theta equals 0 degrees, that's when the loop looks like this. So the magnetic flux passing through it will be a maximum. But when theta equals 90 degrees, that's when the loop looks like that, right? And that's when the flux going through it is 0. So you see, as the loop turns, the magnetic flux going through it obviously changes, and therefore, according to Faraday's law of induction, there will be an induced EMF. And that is how we turn the mechanical rotation, mechanical energy, into electromagnetic energy by creating an EMF. Now we can take a look at what kind of EMF we can produce, okay, using Faraday's law. The magnetic flux passing through this loop would be A dot B. Is A dot B. I can do so because I'm assuming that B is uniform throughout the entire area of the loop. So this is A times B times cosine theta. As you turn, theta changes, right? Theta changes. As a matter of fact, theta is equal to an initial value, theta naught, or theta I, plus omega t, right? If you turn it with a uniform angular speed, omega. So theta will be theta initial plus omega t. And then this obviously is a function of time. This will result in an induced EMF, epsilon, which is equal to negative d phi b dt. Right? Let's see how much that is equal to. Negative AB. Okay, and then you have to take a time derivative of the cosine function. You get a negative sine function. The negative sign cancels. There's an omega, right? There's an omega, and then you turn it into a sine function. Sine omega t plus theta initial. Okay, so you see, as a function of time, the EMF produced is not uniform. Rather, it varies like a sine function of time. Okay, it can be positive and negative. It oscillates. It oscillates back and forth. It changes direction, not just magnitude. And we call this an alternating power source, alternating EMF. Alternating here means the direction of the EMF can go back and forth over time, from positive to negative. Okay, now before I move on any further, I want to ask you this. What if there are more than one turn of loop? Right now I consider only one turn, right? What if I have one turn and then another turn? Just the same shape and size, but I have two turns. Then, of course, both of these turns are cutting through the magnetic field lines simultaneously, and so in each turn I will produce this much EMF, right? What is the total EMF through both turns? Will be twice as much, right? So therefore, if you have n turns, okay, so this loop is made of n identical turns, then the total EMF would be n times this value, okay? Will be n times this value. So you got to put an n here for the most general case. There's an n here. That's something that we keep in mind. Now, if we plot epsilon as a function of t, okay, we're going to get a sine function, of course. Okay, a sine function. So it will look like this. Okay, ever wonder why the power sources, the power grid always delivers electrical current in AC form, alternating form, plus minus, plus minus? It is because in the real power plant, no matter what the initial source of energy is, it can be nuclear, it can be hydraulic, it can be thermal, chemical, whatever you do, you have to turn a coil, which is called a turbine, by the way, in a real power plant, in the presence of a magnetic field, okay, spending those forms of energies to force the thing to turn. And in doing so, you will generate an EMF, and this EMF, as you see, is an AC, alternating source. It's not direct source, which means its direction changes all the time. Okay, so that is why we use AC as a power source. If it is necessary to turn into DC, then there are ways to do that, and that is partly described in our textbook, how we turn AC into a DC. But let's focus right now only on this particular form of EMF, and that is easily, at least in principle, easily generated by turning this coil in a uniform magnetic field, and Faraday's law then give us the alternating current. Okay, there are many other applications of Faraday's law. Many other applications. One of the common features is the so-called eddy current. What is that? Well, suppose you have a piece of bulk materials. Let's say a piece of aluminum, okay, and you put it in a magnetic field, and then when the magnetic field changes, then of course the flux through this bulk piece of metal changes. Or you can take that piece of metal, and you can put it into a magnetic field and push it in and then pull it out, right? Either way, whether you change the magnetic field or whether you move the piece in and out, because in either case there will be a change in the magnetic flux, right, going through this piece. Then there will be an induced EMF, and since we assume this bulk piece of material is made of conductors such as aluminum or whatever, you're going to produce a current. Okay, it will be a circulating current within the body of the conductor. It's called an eddy current. That's what eddy current means. So basically, it is an induced current that live in a piece of bulk material, bulk conducting material, in the presence of a variable magnetic field. And it's got many applications in real life. Now, just like just like any scientific phenomenon, it is always a two-edged sword. Sometimes it's good for us, sometimes it's not good for us. So we can see examples where we wish to avoid it, and examples we wish to take advantage of it. An example where eddy current is good is an electromagnetic stove. Okay, in an electromagnetic stove, I don't know if you've seen it. In an electromagnetic stove, and here is, if I draw something like this, this is the top of the electromagnetic stove. What you see here, you see some markings. There's a piece of glass, and there you see some markings, but there is no open flame of any kind. It's a flat piece of glass, just a flat piece of glass. Okay. Now, in order to cook something, what you do is you put some cooking utensil above it. Now, there is a catch. This cooking utensil has to be made of metal. In other words, conducting material. You cannot use ceramics or whatever. Okay, there is no flame, and you do not simply put electricity through a resistor to generate heat. Okay, that would be simply called the electric stove, not an electromagnetic stove. Okay, so how does the electromagnetic stove work? Well, it works with the Faraday's principle. Well, actually, the electromagnetic stove works on the principle of Faraday's law, and in particular, the generation of eddy currents. Now, what I have here is an area where there's a magnetic field penetrating through. And this magnetic field is produced by a current. It is an AC current powered by the AC power source. Okay, you know, the wall outlet, of course, the AC. So the current is also alternating. Therefore, the magnetic field produced through this region is also variable, right? So you have a variable magnetic flux passing through this region, and then you put some pots and pans on it, assuming it's made of metal. Okay, then as you put this metal piece in the presence of a variable magnetic flux, what happens? Obviously, there will be an induced EMF generated within the metal part of the cooking utensil, right? And since this is made of metal, it can then power a current. That, of course, is the eddy current. Okay, so within the metallic utensil, there will now be an eddy current which will heat it up. So you're not heating up the air directly, okay? You are actually heating up the pots and pans. Of course, that will also heat up the food inside. So you see, it is a simple and yet effective design. There is no open flame. There's very little, relatively little loss of heat into the environment, because you're not heating up the air around it using a flame or using just an electric stove, which is just a resistor. You are using the eddy current to heat up the cooking utensil only. Okay, so it is a rather elegant design to replace conventional stoves. So this is a positive example where eddy current plays a good role for us. Another positive example of eddy current is the so-called electromagnetic damping. Okay, do you recall in physics 1B we did this experiment, damped harmonic motion, right? Damped harmonic motion. Remember how we did it? Remember we had a air track, and then we had a glider. It's supported at both ends, attached at both ends to a spring, and then you pull the glider to one side, let go of it. It's going to oscillate back and forth. Eventually, it's going to stop. Okay, how did we introduce a damping mechanism to stop the motion of this glider? Remember, we taped on either side. We taped a pair of some pieces of magnets, right? Okay, now we told you at that time that the mechanism would become clear in physics 1C. Okay, now you can understand why. You can understand why by taping magnets onto these to the metallic glider, and then as the glider moves back and forth, it's going to cause an eddy current. It's going to cause an eddy current in the track, okay, in the metallic track. And that eddy current, of course, takes part of the kinetic energy of the glider away, right? And that is how the glider will slow down. And the corresponding damping force is, of course, proportional to the current generated, okay? And the current generated, on the other hand, is proportional to the EMF generated, which is in turn proportional to the cutting speed v. Okay, so all in all, the cutting speed v is proportional to the resistant force. And that was exactly what we need, because in 1B we discussed only one type of damping, and that's when the damping force is linearly proportional to the speed. That was realized with our electromagnetic damping. That's why we taped these magnets on. Okay, another example of electromagnetic damping would be an example of how we slow down the oscillation of a needle in an analytical balance. You know a balance, highly accurate balance we use for analytical chemistry. Okay, the needle would just go flip back and forth. Takes a long time for it to slow down and stop. Right? It's annoying. So how do we make it slow down faster and stop faster? Well, what we can do is, first of all, the needle is made of metal, right? We make sure the needle is made of metal, and then we put a magnetic field through it like this. So as the needle swings, it is actually cutting through magnetic field lines and therefore generating an induced EMF, right? That induced EMF powers the current through the metal part, and therefore taking energy away, because the current will generate heat, and that heat, of course, ultimately comes from the kinetic energy of the oscillation. Okay, so the oscillation will die down quickly, and that is an example of electromagnetic damping. Okay, now here is a bad example of eddy current, something we wish to avoid, and that is the so-called overheating in a transformer. When you buy a piece of electronics, such as you know, a CD player, whatever, you know, even those little portable electronic devices, such as a CD player, it always comes with an AC power source or a charger, right? And that AC power source is usually not just a simple plug, rather it has a it's got a bulky cube piece, right? And you plug it in, and this thing heats up a little bit. Remember that? It heats up a little bit when you plug it in. What is the inside? Well, it turns out most electronic devices do not operate directly off the power grid. It does not usually operate at 110 volts AC, which is what our power grid gives us. It usually operates at a lower voltage, and so we need to convert a high voltage to a low voltage, or sometimes from low to high voltage. Either way, when we convert voltages, we need something called a transformer. We will learn in a later chapter. But there's a problem with a transformer. In a transformer, you have to use Faraday's law, okay, in order to change you know, the input and output voltage. And in doing so, there will be an induced EMF that will run in a piece of bulk metal, okay, which is typically made of iron, in order to increase the magnetic flux. And the problem with that is that it can cause the iron piece to overheat due to the eddy current. So you run into a danger of overheating the transformer. How does one avoid that? How does one reduce the effect of eddy currents? Well, in a transformer, in the core of the transformer, instead of a piece of, you know, just solid piece of iron, which has very little resistance, what we do typically is we take these iron pieces and we separate them into much smaller pieces, okay, using insulating materials. So we get insulation layers. And so these are insulation layers, okay, and in between two neighboring pieces of conducting iron, we put an insulation layer. So imagine if there's an eddy current. Okay, without these insulation layers, you get a whole piece of iron, and there's a giant eddy current flowing like this with very little resistance, so you can generate a lot of heat. Okay, a lot of heat. Remember, the power turned from electrical power turned into heat. Given epsilon r, it goes like epsilon squared over r, right? If r is small, for the same epsilon, you can get a lot of thermal power generated. On the other hand, if you break into small pieces, then since current cannot flow from one piece to the next due to the insulation layer, you break the eddy current into much smaller loops. Okay? And due to the much smaller size of the loop, each loop has much greater resistance. Okay? You just make the path really narrow, then you increase the resistance, right? So R effectively can increase a lot, and therefore the thermal power generated by the eddy current can go down. That is how we avoid overheating a transformer. Okay, so these are just, you know, a couple of common examples of eddy current and of Faraday's law of induction. There are many other examples in real life. Okay, what I want to do now is, before we close this chapter, now that we're already in the third part, we still have some time, I want to discuss a couple of further examples involving applications of Faraday's law of induction, because you know, it takes, this is one of the difficult, rather comparatively speaking, more difficult chapters in 1C. So I want to give you more opportunities to practice. Okay.